Ladies and gentlemen, welcome to video lecture number 8 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in Paris in late 2017. We are today on October 9th of the year 2018, about a year later. This video now concentrates on the suggested basic icosahedral arrangement to be matched with solar phenomenology. It is an icosahedral arrangement which is based on 12 spherical balls. The model which is proposed for the fivefold symmetrical geometry, which is envisioned in the Sun, is this. You see a spherical glass envelope which has a certain radius, a certain diameter. In this spherical envelope fit a certain number of smaller spherical balls. We shall see how many there are. And these balls are mutually tangential. For instance, this ball is tangential to each of its 5 next neighbors. And this holds for each of the balls in this arrangement. There is a ball at the top, which we can call a polar ball, say a north polar ball, and a ball at the bottom, which we can call a southern polar ball. Now you see a ring here in this plane of a certain number of balls. If I turn the ball around, the sphere around, you see that there are 5 of them. And then there is a lower ring with as many balls. There are again 5 of them. These 2 rings in all are composed of 10 balls. Then we get a total with the 2 polar balls of exactly 12 balls. Now each of these spherical balls is also exactly tangential to the outer spherical envelope. This, in principle, is a set of 12 balls that are located about a general equatorial plane that divides an upper or northern hemisphere from a southern lower hemisphere. If we now withdraw the top ball, and if we look into this arrangement, we shall see that there is a cavity. There is a cavity which is symmetrical, isotropic in all directions. Because the spheres are mutually tangential and tangential to the outer envelope, you see that there is not much motion among these spheres when I hold this arrangement in any position. And in theory, if the arrangement was implemented perfectly, there would be absolutely no motion. This is called geometrical frustration and is due to the fact that there is a tangency among all of the objects that are assembled. So these 12 balls are mutually tangential. They are tangential to an outer spherical envelope, but they are also tangential to the imaginary surface of the internal cavity. Of course, we cannot see this in this model, but this is how it is. This is a unique setup which is possible only for exactly 12 balls. The cavity's radius is not free. There is a unique value for this radius, and it is 0.31, etc., of the radius of the outer spherical envelope. So we have a unique arrangement, which is the one that is proposed to be matched against the actual phenomenology of the Sun. Now we are interested in exploring a little bit more what is inside this arrangement. For this, we will now use a set of transparent balls in the transparent outer sphere. In this set of transparent balls, now you can see that their diameters, in the way it is here arranged, they all point to the center of the overall sphere. And the centers of these equators, you see the equatorial line on each of the balls. The equatorial line is defined by the equatorial plane, and it is perpendicular. This equatorial plane of each smaller ball is perpendicular is at a right angle to the radial line from the axis of this smaller sphere to the center of the overall sphere. So if we now look a little bit more at this equator, we find that this equator of one of the 12 smaller balls, which lies in this approximate plane, includes the center of the ball, of the smaller ball, which is approximately where I hold this red stick. Now the blue stick stands for the equatorial plane of the smaller ball, which is the polar one, and the red stick at its intersection points to the center of this ball. As you can see, this center is at a certain distance between the outer surface of the overall sphere and the center of this overall sphere. As we shall see, this distance is strictly defined by the geometry of the arrangement, and the distance from the center is 0.655, etc., radius fraction of the radius of the overall sphere. So if we now consider the set of 12 such centers, there is a spherical shell, a spherical surface that passes through these 12 points, which defines inside a sphere in the interior of the larger sphere with a radius 0.655, etc., of the radius of the overall sphere. This sphere is so defined again by the centers of each of the 12 smaller spheres. The relation with the icosahedron is that there is in fact one of the icosahedron's vertex at each of these centers. So the intersection between the blue stick and the red stick coincides with the vertex of an icosahedron, and the other 11 vertices of the icosahedron are in the centers of the other 11 smaller balls. This is what is called here in the Fivefold Sun the solid body vertex of the Sun, each of these 12 vertices, and it amounts as a set of 12 vertices to what we call the basic icosahedron. We can see on this model a polar vertex at the top, a polar vertex at the bottom. In the upper ring here we see 5 vertices, and here in the lower ring we see 5 vertices. So if I now put on top of this vertex a half sphere, you have an idea of how is composed the arrangement of 12 outer spheres that I showed in the preceding page. Of course, you have to imagine a sphere on each of these vertices, and in each case the vertex is the center of the sphere. Also, you see in this icosahedron its edges, which are in blue here, and its faces, which are delineated by 3 edges. Here is the face of the icosahedron, and which is also located between 3 vertices. So here we have an icosahedral geometry which is fully defined by this set of vertices, edges, and faces. If we want now to inquire into the possible fit of such a geometry with actual phenomenology of the Sun, we have to know which are the geometrical parameters of such an icosahedron. The suggested 12-ball icosahedral clusters geometrical parameters are defined by the radius of a central cavity. Again, it is 0.3108, etc. If this was the case in the Sun, we would have a radius of this radius fraction inside the Sun. The circumradius of the basic icosahedron, which I said in the preceding page, is defined by the distance from the center of the large sphere. In the case of the Sun, this would be the center of the Sun. And any of the 12 solid body vertices which coincide with the icosahedron's vertices, it is 0.655, etc. of the radius of the outer sphere, the overall sphere. The radius of the central cavity, defined as a function of the radius of one of the 12 outer balls, it is 0.902, etc. This is defined by this formula, which was published by Linus Pauling, the Nobel Prize laureate in chemistry, in 1947. We are happy to have Pauling's investigations of the structure of icosahedral compounds in chemistry, which yielded some fundamental formulae like this, which will help us in understanding how this extremely simple arrangement is constructed. The diameter of a 12 ball as a function of the radius of the larger outer sphere. In the case of the Sun, this would be as a function of the radius of the Sun. It is 0.689. So this is now the end of video 8. In video 9, we will explore the angles in between the characteristic points and lines and surfaces in the suggested icosahedron, and see how these exist in this structure that we propose for the Sun.